Hello everyone, it's a pleasure to be here virtually at Computer Graphics International 2020. I'm Yuliang, a PhD student from Zhejiang University of Technology. Today I will talk about our recent work on indoor scene point cloud segmentation using page graph convolutional network. Indoor scene semantic segmentation, in which indoor layouts and objects are assigned with different labels, is a crucial task in scene understanding. It is also fundamental to indoor scene applications such as indoor navigation, robotics, augmented reality. It is still challenged due to incomplete raw inputs, the scale of the point cloud data, cluttered and always heavily occluded in real-world indoor environment. For effectively processing point clouds, the essential issue is how to effectively extract the feature information of point cloud scenes or 3D shapes. Conventional segmentation work can be divided into two types. One is based on data or models. Another one is based on geometry primitives. Model-based methods find and replace the scanning data with models. Primitive-based methods is considering geometry abstractions or representation of indoor objects. Deep learning has achieved significant success on 2D image processing, inspiring works in 3D space. Most previous methods address 3D geometry and 3D vision problems using voxels or multi-view images as inputs of CNNs. The conversion from discrete point clouds to such regular representations is always time-consuming. Recently, PointNet introduced a pioneer work which has a significant impact on employing CNNs directly on point cloud data. Most deep learning-based methods focus on extraction of intrinsic features for individual points and their neighbors within bounded range. Moreover, when applied to indoor scene understanding, these methods have to partition the whole point cloud scenes into blocks with limited point size. A fundamental observation in various cluttered indoor environments is that man-made objects are always constructed in a highly structured style, with a combination of various surface patches. The discrete sampling points in the surface patches remain geometrically consistent. Apart from dominant room layouts, the surface patches can also be identified in indoor furniture such as tables, chairs, and cabinets. The discrete sampling points in the surface patches remain geometrically consistent and can be considered as object parts. The key idea of our work is to use surface patches as data representation and construct a scene patch graph. Considering patches as nodes and their spatial relationships as edges, we incorporate patch graph convolutional network for semantic segmentation task. The pipeline of our method can be seen from this figure. Given indoor scene point clouds, we first generate surface patches from input point cloud by region growing strategy, and then compute figure descriptor for each surface patch. Then an initial scene patch graph can be constructed using the surface patches and their pairwise relationships. The network consumes the graph and encodes multi-layer edge features through dynamic graph construction and edge convolution. The network finally outputs semantic labels for each point of indoor scenes. The first step is scene patch graph construction. Given an indoor scene point cloud as input, we convert the input into surface patches using region growing. Specifically, region growing for a patch starts from a seed point and add a new point if this point is close to the patch surface with similar normal. For each surface patch, the fitting rectangle is generated through projecting the bounding box onto dominant axis. For each fitting rectangle, the feature descriptor includes central point position, normal, height, length, area, color, ratio of length to width, fill ratio of convex hole area to area, and boundary. The initial scene patch graph is constructed where nodes are surface patches and edges represents the pairwise patch spatial relationships. Patch descriptors are employed and combined as node features, which indicate compressed representation of input patch. In order to extract features, we adopt dynamic graph convolution operation since it can capture semantically similar structure at each feature embedding, even they may be distant in the original input graph. Our dynamic graph convolution consists of two types of layer, that is, dynamic edge layer and edge convolutional layer. In dynamic edge layer, we recalculate the graph edges using KNN based on distant matrix in feature space. To enlarge receptive field without loss of resolution or coverage, we use dilated convolution concept. We also use top K polling operation for downsampling. In edge convolutional layer, we apply convolutional-like operations on edges connecting neighboring nodes. We concatenate node feature and relative feature. To generate new features, we use MLP as activation function and max operation as aggregation function. In order to extract local contextual features of point cloud, it is beneficial to process graph data through multiple levels. Our dynamic graph unit, which incorporates dynamic edge convolution inside a U-shaped encoder-decoder. The encoder consists of a dynamic edge layer and an edge convolution layer. Our dynamic graph unit consists of multi-level encoding blocks and corresponding decoding blocks with skip connections. The architecture of our network for indoor scene semantic segmentation is presented as you can see. The initial scene patch graph is fed into dynamic graph unit module that carries out hierarchical edge features aggregation. These edge features are concatenated with patch features. Subsequently, an MLP block is used to predict label of each patch. This block has three shared full connected layers to predict label of each node, incorporating batch normalization, dropouts, and value activation. This network finally outputs semantic segmentation of input scene. Based on patch features, we argue that most patches can be classified into layout or object. The classification can be regarded as a coarse segmentation, which is presumably beneficial for final range segmentation. Regarding layout object classification information, indoor scene semantic segmentation network is constructed by the same architecture of PGCNet. To be more specific, layout object classification information is concatenated with the hierarchical features from dynamic graph UNet before MLP patch prediction block. The first table presents quantitative results of our method and comparisons with state-of-art methods on Array 5 of S3DIS dataset. Here we adopt our layout object-aware PGCNet for indoor scene segmentation. PatchMLP donates a MLP classifier using our extracted surface patches and their features. The MLP classifier is the same one as in PGCNet. It can be seen that PatchMLP can achieve similar performance as PointNet, especially in room layout classes. This suggests our surface patch representation has the advantage of retrieving room layout structures. The results also clearly show our PGCNet framework performs comparable segmentation results with much faster training process. Notably, we perform particularly better in ceilings, floor, and wall, as well as objects that is not easy to distinguish from room layouts such as bookcase and board. This is presumably due to our patch representation and layout object-aware training. On the other hand, our framework could not perform accurate segmentation as other competitive methods for segmentation of interior objects with complex shape, such as sofa. The second table shows labeling accuracy results on ScanNet. The rich labeling of ScanNet makes semantic segmentation more challenging. Using patch representation, our framework can successfully segment major layout structures and main indoor objects. Our proposed framework outperforms PointNet and achieves similar overall accuracy as PointNet++. Here are some segmentation results on various types of indoor scenes. Given input indoor scenes from S3DIS dataset, our method first generates surface patches. Our PGCNet framework is able to correctly classify room layout, including ceilings, floors, and walls. Open doors are almost labeled correctly in these scenes, while columns are difficult to distinguish from walls. Most indoor objects such as tables and chairs can be retrieved as well. The patches pasted on the wall are difficult to fully segmented, which might be part of bookcase, board, or clutter. These figures show visual comparisons of segmentation results on various indoor scenes. Notably, our method correctly segments door while others cannot. Our scene patch graph representation carries out more smooth results than others, for example, bookcase and table. As seen from the first table, the training time of two other methods in our implementation on the same GPU is around 13 hours and 4 hours respectively. In comparison, our SimPatch graph-based training time is only 6 minutes, which are much faster than pointwise training. In the second table, we present the data of running time in seconds for each step of indoor scene semantic segmentation test. The main computation time is patch generation, since the whole point clouds are taken as input. The patch label prediction is only 0.5 seconds, owing to the patch representation of indoor scene. The ablation study suggests that the proposed dynamic graph ViewNet module is significantly improves network's ability of patch feature extraction. It can also be observed that the dynamic edge layer does play an important role in the final performance. Here in this work, we introduced a novel framework named as PGCNet, which takes the surface patches as data representation of indoor sim point clouds. This representation can largely reduce the data size and also enable us to apply graph convolutional network architecture on such large-scale point clouds. We also introduced a new module to capture and aggregate hierarchical edge features. This module employs dynamic edge construction and edge convolution at each encoding block. The network training is effective, and the performance is competitive on the segmentation of public indoor scenes. In the future, we plan to further improve patch generation and extended our network to other indoor understanding tasks, such as instance segmentation. That's all for this presentation, and thank you for your time.